Hello students, myself Professor Manu TM from KLE Institute of Technology Hubli. See, I will be dealing with Model 2 according to your VTU syllabus in Analog Digital Electronic Circuit. Students, in the previous class you might have studied all analog type of circuitries, but in this class I will be dealing with the basic gates that are used to implement the bigger digital circuits like. So basically, sir, in the previous class, sir might have explained what is analog representation. So in this class, just I'll try to highlight how the digital representation will be there. Like, so in a digital representation, we'll be using a discrete type of signals where the information is available at the discrete instants of time, like for which we call it as discrete signals. Or the for these signals, the value will be assigned in terms of binaries called as 1 and 0. 1 and 0. So the major advantage of representing in terms of digital values or binary values are, see, these type of gates supports programmability, and it give the circuitries will give more reliable one, like reliable type of output, in the sense for any condition the output will not change, because in a digital representation the signal the value representation will be having a noise margins, like in the meaning is in terms of binary values, like logical 1 will be allotted with a 5 volts value, and for logical 0 it is 0. But in practical circuits we will be having a range of voltage. If the voltage ranges between 3.4 to 5 volts, means we will treat that is equal to a logical 1 output. If the voltage ranges from 0 to 0.6, means still we call it as a logical output is equal to 0. If any variation is there in the output current because of temperature, means still the value of 1 and 0 lies well within the 5 volts. That's why the output of that circuit will never change if I operate the digital circuits many times. This is the biggest advantage that we have in terms of representing in kinds of digital forms, like. So by giving this type of an introduction, by giving this as an introduction, I'll start to review the basic circuits that are studied in first year, like in the sense in basic electronics. Like you already studied the basic gates in case of basic electronics. Just I'll try to revise the basic gates, what all the different type of basic gates that we are using it, and how best we can utilize those basic gates to build a bigger logical circuits. Like the gate is a one for which you can have multiple inputs, but the gate will give you only a single output will be there. Like a logical gate is nothing but a digital circuit with one or more inputs and has only one output, like. So logic gates are nothing but the fundamental type of building blocks which will be used to design a digital systems. Like by interconnecting these various type of basic circuits, we can build a bigger circuit by which I can do some arithmetic and logical type of operations, like. And these operations of these circuits can be easily understood by using the truth table representation, where in which you will be representing the input variables as well as the output variable, like. So depending upon the number of logical input variables, we will be having a combination of different values in terms of the logical variables that you are chosen, like. So these things we'll try to see it later. First I'll try to tell you what all the basic gates that we have in terms of digital circuit representation, like. The first one is nothing but a NOT gate, another one is an OR gate, and the third one is nothing but an AND gate, like. Just we will see what is a NOT gate and how the representation will be there in terms of symbolic representation, like. So usually in the NOT gate is NOT gate. The symbolic representation of NOT gate is this, like when I give a logical variable like A as an input, I'll be getting an output is equal to Y. So usually, as I said before, the output of this will be represented in terms of truth tables to understand how this functions, like. A, the left side will be having an inputs and the right side we will be having an output, like. Because only one variable is there, like if I give an input is equal to 0 to this logical variable, means that NOT gate will give an output is equal to 1. When I give an input is equal to 1, means naturally the output will be equal to 0. Okay, so in terms of expression, I can write it as this is equal to not A, or Y is equal to A bar. In some books, they will write it as something like A dash. This is a logical expression in terms of NOT gate, like. See, basically, this gate This operation will be implemented by using a TTL series with a number is equal to something like 7404, like this is an IC number in terms of TTL logic. So if you want to verify whether this IC is working with respect to a NOT gate or not, means we have to utilize in a practical case by using an IC number is equal to 7404. So which is having the IC format with respect to this is something like this, which will be having totally 14 pins. 1, 2, 3, 4, 5, 6, 7. This is 14, 13, 12, 11, 10, 9, 8, 8. See, 7 is nothing but a ground. In laboratory, we have to connect this pin to a ground, and this is for 5 volts. See, 1 and 2, 3 are nothing but a pins. It is totally a 14 pin IC, 13, 12, 11, 10 and 9 and 8 like. So these are nothing but the pin numbers. The IC number in terms of NOT gate is 7404 like. So here with respect to NOT gate, this is one NOT gate. Pin 1 will be the input pin and pin 2 is nothing but an output pin. So like that we have totally 6 NOT gate within this IC. If you want to verify this, means what you have to do in a practical sense is give an input to this and see what is the output that you are getting here like. Okay. See, this is 13 is an input pin and this is output pin. This is 13, something like this. So this is an IC, the TTL IC 7404. We can use it to check whether this is working with the NOT gate or not like. So this is a simple gate that we have in case of digital circuit. The next circuit the gate that I will discuss is an OR gate like. OR gate is a simple basic gate. So the symbolic representation of this OR gate is this. A is an input, B is nothing but another input that we will be giving, and we will be getting an output is equal to Y. A and B are nothing but a logical variables. It can take either 1 or 0, for which you will be getting an output is equal to Y. As I said before, the operation of this circuit will be represented in terms of truth table. Truth table here like. So just I'll try to write the truth table, which is having an input variables is nothing but A and B, and the output is nothing but an Y here. Okay, because we have two variables A and B, the input combination that I can give is 0 0, 0 1, 1 0 and 1 1 here like. There is another way of representation also in terms of this logical variables like A and B, that is the low low, another one is low high, another one is H L, that is high and low, and H H. This is equivalent representation in terms of binary values like 1 and 0. So in terms of an electrical sense, 0 is nothing but a 0 volt and 1 is nothing but 5 volts. See, this is another way of representing it like. So according to the logical operation of an OR gate, when I give an input is equal to 0 0 means the output that I will be getting is 0. With respect to this gate like 0 and 1 means the output with respect to this gate is 1. 1 and 0 means the output is equal to 1. When both are equal to 1 means I will be getting an output is equal to 1 like. So this gives an output is equal to 1 if and only if any one of the value is equal to 1 means I will be getting an output is equal to 1, or if all the values are equal to 1 means the output will be equal to 1 like. See, another way of representing is L means the output is equal to L. If any one of the input is equal to high means the outputs will be equal to high. This is nothing but OR gate representation or truth table. So we will represent this truth table in terms of a logical expression, that is equal to Y is equal to A or B. This is in terms of Boolean expression like, in terms of Boolean expression, or otherwise we will be writing A plus B, A plus B. So the equation in terms of an OR gate is Y is equal to A plus B. So just we'll try to substitute the values and we'll check it out whether what is the value that we will be getting here like. When A is equal to 0 means and B is equal to 0 means the 0 plus 0 is nothing but 0. So 0 plus 1 means the output will be equal to 1. Like that we can evaluate what is the output that we get from this expression A plus B. See, for this we have an IC with respect to TTL series is nothing but 7432, in which we have 4 OR gates. OR gates, again it is a 14 pin IC. So in that we will be connecting 7th pin to a ground and 14th pin to a 5 volts here like. See, in that particularly because it is having 2 inputs here, so we will be connecting 1 and 2 to OR gate, and the output will be equal to the 3rd pin like. So like that the connections will be made. Totally we will be having 4 OR gates in 7432. This is 7432 is an TTL IC. So in the laboratory what we do is just we will take the 74332 and we will be giving 1 and 2, we will be using 1 and 2 as an input pins, and 3rd pin we will be getting an output like. Depending upon the requirement of this OR gate, we can interconnect between the other gates to check out what is the output that you will be getting it like. See, this is basically an OR gate in which the output table is something like this. Okay. So the next gate that we will be seeing is the next basic gate that we have is an AND gate representation like AND gate. The symbolic representation of AND gate is this, in which 2 inputs will be there, that is A and B will be giving as an input, and the output that we will be getting is Y. So I will try to write the truth table with respect to AND gate, that is A and B are nothing but 2 input variables, and for which I will be getting an output is Y. Whenever we have 2 logical variables like A and B, means we will be getting 4 combinations as an inputs here like, that is when A is equal to 0 and B is equal to 0, what is the output that we will be getting it? When A is equal to 0 and B is equal to 1, what is the output? Like that we have another combination like 1 0 and 1 1. When A is equal to 0 and B is equal to 0, the output that we will be getting is 0. When it is equal to 0 1 means the output is equal to 0, and this is also otherwise also we will be getting an output is equal to 0. When it is equal to 1 1, the output will be equal to 1. The meaning of this is, if all the inputs of A and B is equal to 1 and 1 means the output will be equal to 1. That means if and only if A and B is equal to 1 means the output will be equal to 1. This is the characteristics of AND gate. Usually the Boolean expression with respect to AND gate is A and B, we will be writing it, or otherwise we will write something like A dot B. This is a logical expression for an AND gate here like, and A and B. See again, see in practical applications we will be using a TTL gate, TTL IC, in which again the arrangement of these logical gates in terms of an IC, we have total 4 gates like this. Again the 7th pin will be connected to ground and 14th pin will be connected to VCC. Again, say 1 and 2 will be the input with respect to an AND gate, and the output will be 3. Like that the interconnections are made in terms of using this AND gate in terms of this IC to evaluate what is the output that we will be getting it like. So usually if I want to implement a bigger circuit, means we can utilize those 4 AND gates and we can interconnect it like. See, other than these basic gates like AND gate, OR gate, NOT gate, we have another one basic gate called as an exclusive OR gate like, exclusive OR gate. Exclusive OR gate. See, before going for this exclusive OR gate, see in fabrications we will be fabricating these basic gates, particularly OR gate, AND gate, with more number of input pins, but it will be having only one output pin like that. Because of that we call it as a gate, logical gate like. Okay. So next we will see what is an exclusive OR gate like. This is a little bit of higher basic gates. So the symbolic representation of this gate is like this. The A, we will be giving 2 inputs like A and B as a logical variables, and the output that I will be getting is nothing but an Y. So let us see the truth table with respect to this exclusive OR gate representation. Exclusive OR gate, just I will rub off this and I will try to write the truth table with respect to exclusive OR gate. Exclusive OR gate, see A and B and the output is nothing but an Y here like. So 0 0 0 1 1 0 and 1 1, because we have two logical variables A and B. And the output that I will be getting is when it is equal to 0 0, when A is equal to 0 and B is equal to 0, the output that I will be getting is 0. When A is equal to 0 and B is equal to 1, the output is equal to 1. And when A is equal to 1 and B is equal to 0, the output is equal to 1. When both are equal to 1 means the output that I will be getting is 0. So if you have odd number of ones in the input means you will be getting an output is equal to 1. When even number of ones are there means the output will be equal to 0. So this gate is having a significance in case of communication system, particularly to check whether you got any error in the output which is transmitted from the transmitting station. For example, if I want to transmit something like 1001 means they will add the parity bit like. So what they will make is they will add one more parity bit such that it will become an even parity information which has to be transmitted to the receiving end, receiver station like. If any change is there, something like suppose say this bit is been changed to 0, 1 0 1 1, the parity is now changed here like, the parity of this is equal to odd 1 like. See, from that we can understand that there is a change in the in terms of whatever the information that is transmitted like. So you can observe here we are transmitted 1, but at the receiving station it is received 1 like, 0. So from that we can understand that there is an error here like, that is the significance of this exclusive OR gate like. So we can utilize in communication system to find out is there any error that is occurred while transmitting to the receiving station like. Okay. See, we have one more a gate called as exclusive NOR gate. Usually we call it as a XNOR gate like, XNOR gate. So the symbolic representation of XNOR gate is something like we put a bubble in front of that, it indicates that it is an complementary type of circuit like, for which we will be giving A and B as an input and the output that I will be getting is Y. See, this is a complementary type of gate like, the output that I will be getting with respect to this gate is, so when it is equal to 0 0, the output is equal to 0 0. When at 0 1 means the output is equal to 0 and this is equal to 0, and the when 1 1 is there means naturally the output will be equal to 1 like. When it is equal to 0 0, the output is equal to 0. When even number of ones are there means naturally the output is equal to 1, and when odd number of ones are there means the output is equal to 0. It is exact complementary to exclusive OR gate like. This again we will be using this gate for logical, the significance of this circuit is we can use it to find out whether the even number of ones are there as an input or odd number of ones are there as an input like. So the next we have an universal type of gates called as NAND gate and a NOR gate like. So these are nothing but an universal gates. The meaning of universal gate is we can realize in the sense implementation of any logical expression by using only the NAND gate and a NOR gate. That's why we call it as an universal gate like, whatever may be the length of the logical expression, the entire logical expression can be implemented only by using a NAND gate and NOR gate. So there is an advantage of using only the NAND gate and NOR gate for realization is, just I'll try to justify like why we call them as an universal gates like. So as you have seen in the previous ICs like in case of OR gate and an AND gate, you have only in TTL IC you have only 4 AND gate or an OR gate in a particular IC like, but you don't have something like AND gate and an OR gate in a same IC, So suppose say we have a logical expression, if it is implemented by, for example, I will try to write a circuit like this. Suppose say this is one circuit, a logical circuit for which I will be giving an AB as an input and CD as another input here, for which I will be getting an output is equal to Y. See, if you want to implement this circuit by using those ICs means naturally I require two ICs here. One is with respect to an AND gate, another is with respect to OR gate. Like, so I require two ICs here. Like, the same logical circuit can be realized only by using a NAND gate or NOR gate, like, so that you can save the space that is required for an AND IC as well as an OR IC. So if I realize it by use only NAND gate, means I can use only one NAND gate to realize the entire circuitry of this. That's why NAND gate realization or only NOR gate realization is having an advantage, like, that's why we call them as an universal gates, like. So just we will see what is the truth table with respect to NAND gate and a NOR gate, NAND and NOR gate, and we will try to represent the basic gates in terms of NAND gate and NOR gate realization. NOR gate realization. These are called, as I said before, NAND and NOR gates are the AND gate and NAND gate and NOR gates are called as universal gates, like. So just we will see the truth table with respect to NAND gate and a NOR gate, and I will take a simple logical expressions or the basic gates to realize using only NAND gate and NOR gates, like. NAND gate, the symbolic representation is A and B. If I put a bubble in front of that, means it is nothing but an inversion here. So the basic other way of representing is I will be using an AND gate. If I put a NOT gate in front of that AND gate, means you will be getting a complemented. This is equal to Y. This is also other way of representing it, like. So the logical expression with respect to this is Y is equal to A B whole bar. So the meaning is I will be giving A is in one input, B is in another input, that is A and B. Because I have put a bubble here, like, it is the entire expression is complemented there. This is Y is equal to A NAND NAND B operation, like. The truth table with respect to this is, the truth table with respect to NAND gate is truth table of NAND gate. So as you know, we have two logical input variables. When I give an input to these logical variables, means I will be getting an output is equal to Y. Whenever we have two logical variables like A and B, means the number of values that it can take is 0 0, 0 1, 1 0 and 1 1. It's completely complement of an AND gate here, like. So when I give 0 0, means the output will be equal to 1, that is complemented. If I substitute the value, that is, suppose say A is equal to AB bar. If I substitute value is equal to 0 and B is equal to 0, means the net value is 0, 0 is complemented, means I will be getting an output is equal to 1. So when it is the input is equal to 0 and B is equal to 1, A is equal to 0 and B is equal to 1, means just I substitute the value here 0 and 1. 0 into 1 is nothing but a 0. If I complement that, means I will be getting is equal to 1. So this is also equal to 1, and when both the inputs are is equal to 1, means the output that I will be getting is equal to 0. This is the truth table of NAND gate, like. NAND gate. So next is a NOR gate. Just we will see what is the symbolic representation of NOR gate, and we will try to write what is the truth table with respect to NOR gate, like. So this is the NOR gate is the symbolic representation is I will be giving two inputs like A and B, and I will be getting an output is equal to Y. This is just a symbolic representation. The equation, the Boolean expression for this is Y is equal to the inputs that I have given is A plus B, and this is complemented. It is as good as the representing in terms of something like A and B. Okay, and if I connect a NOT gate to this, means it will become a NOR exclusive NOR gate, NOR gate, like. A and B is equal to this. So now we will try to write a truth table with respect to the NOR gate, like. So NOR gate truth table is truth table when see I have two input variables like A and B, and I will be getting an output is equal to Y. If both A and B are there, means naturally 0 0, 0 1, 1 0 or 1 1, or I can write L L or LH. HL and something like HH in terms of high value and low value. 1 means high, 0 means low value. So when this is equal to 0, 0, so 0 plus 0 means it is 0, a complement of that is equal to 1. So 0 when A is equal to 0, B is equal to 1 means the 1 complement of that is equal to 0. Again, either way, like A is equal to 1 and B is equal to 0 means if complement of that is equal to 0. 1 plus 1 means naturally this is 1 again, complement of that is equal to 0. This is to table of NOR gate like. See, these basic gates plus the universal gates will be utilized to build a bigger logical circuits here like. See, as I said before, these NAND and NOR gates are nothing but an universal gate, means by using these NAND and NOR gates we can build some basic circuits. Instead of using something like OR gate and a AND gate, we can utilize only the NAND gate to build in any logical expressions. So just I will take up some of the basic circuits and try to realize it by using only the NAND gate and an OR gate. We will take an example and try to do that like. So in practical with respect to TTL ICs, we have 3 input ICs also like, for which you will be having only one output. Okay. It depends on how do you fabricate in terms of getting these logical circuits to build a bigger circuits like. See, first I will use a NAND gate to realize the basic NOT operation, realize the basic NOT gate. That means I will be using a NAND gate to work like a NOT gate here like. Okay. So as you know, the NAND gate representation is something like this, A and B, and the output is equal to Y. The logical expression for this is equal to AB whole bar like. I wanted to use this gate as a NOT gate like. So what I do is I will take the same NAND gate. Instead of connecting another input like B, I will try to connect it to A itself like. If I use like that means I can write Y A and A whole bar. So A into A is nothing but a simple A complement of this like. So now if I connect this NAND gate or if I short this A like this means I will be getting Y is equal to A bar. So now this NAND gate is working like a NOT gate. So like this we can realize an AND gate also. So AND gate, just I wanted to realize this AND gate by using only the NAND gate. I will not be using any other gates here like any other gate to realize the AND gate. What is the function with respect to Boolean expression with respect to AND gate means it is A and B. I wanted to realize this A and B by using only the NAND gate here like. So what I do is I will take NAND gate like A and B are the 2 inputs here. The function that I will be getting with respect to NAND gate is AB whole bar. So what I need is AB, that is AND gate equation. So what I do is I will take another NAND gate and try to connect like this. So AB I have, and if I, because there is a bubble, that means NOT operation means I will be getting one more bar above this like. What is the resultant one that I will be getting here? It is AB. Now the combination of 2 NAND gates with respect like this will give you an AND function here like. So like that we can design the basic AND gate by using only the NAND gate here, NAND gate. Next we will see how we can realize the OR gate by using only the NAND gate here like. Basic NOR gate only by using NAND gate. See what is the function with respect to OR gate? Y is equal to A plus B. Y is equal to A plus B. This I wanted to realize it by using only the NAND gate like. So what I do is, say I will double complement this Y. So what it remains? Again I will be getting Y only. So same thing I will try to do with respect to right hand side. I will double complement this like. So you will left with only a plus b. So what I do is I will try to keep this upper side bar as it is, and whatever it is there below, that is this, I will try to simplify by using a De Morgan's theorem. So I hope you might have studied in basic electronics what is a De Morgan's theorem. Just in the next session I will try to explain what is the rules and what is the De Morgan's theorem also. In this class just I will try to explain like this. So by using a De Morgan's theorem I can write a bar into b bar and whole bar, just I will keep it as it is like. Now you have a dot operation, means I can realize it by using NAND gate like. See, if I take a basic expression of a NAND gate is a and b whole bar like. The operation that we do in between the two logical operation is a product term or dot operation like. So if we don't have any plus operation in between, this means logical variable means I can easily realize by using NAND gate. What you need to do is take a logical expression which is having a plus sign, apply a De Morgan's theorem such that you will be getting dot in between the logical variables or maybe between the product terms like, so that it can be realized easily by using a NAND gate. This is a simple technique that we need to use it when you wanted to realize it by using a NAND gate like. So now you have an expression which is of form, I can use it to realize it by using NAND gate easily. So what I do is first I will try to implement a bar, next b bar, and then automatically if I connect it to a NAND gate means you will be getting a plus b easily. So first what I do is I will try to connect like this. This is a by using only the NAND gate here like. So what is the output that you will be getting? A bar. Okay. So I will take another gate, I will connect another variable like b. So what is the output that I will be getting? It is b bar. So now what I do is, say a bar I have, b bar I have here like. What is the operation that you are doing here? It is a product term. So which gate will do the product term operation here like? Again I will be connecting one more NAND gate here like. So the inputs for this NAND gate is a bar and for this it is b bar. So I will be getting a bar dot b bar and whole bar, because you have a bubble means it always represents a negative complement representation. So a bar dot b bar means you will be getting this is equal to a plus b. This is how you can realize all the basic gates by using only the NAND gate like NAND gate operation. See, just I will take another example of realizing an exclusive OR gate by using NAND gate only. So this is very important for further realization of bigger circuits by using only the NAND gates and NOR gates like. So see, exclusive OR gate, say XOR gate, just I will take this expression and I will try to realize it by using a NAND gate like. So just I will tell you the technique how to realize it by using only the NAND gate. See, the expression, see I have written a truth table with respect to this like truth table, that is a is equal to 0 0, I mean a is equal to 0 and b is equal to 0, something like this. 0 0 0 1 1 0 and 1 1 means whenever this is the logic truth table with respect to exclusive OR gate like. See now the Boolean expression with respect to this is, we will see how to write the Boolean expression in the later while discussing the combinational circuit like. Just try to write the equation directly, that is a dash b and a b dash like. So this I will try to realize it by using only the NAND gate like, realize it by using only the NAND gate operation. So what we do is, in truth table or the expression that I will form only for the truth values which are present in the truth table like. Truth table in the sense wherever the output is equal to 1 we call it as a truth function. What you do is you try to combine these logical variables in such a fashion that if I substitute the values for this a and b means the output should be equal to 1. The meaning to say is I am combining a and b. See, if I write something like a bar b, that is I am combining these logical variables with a bar b means if I substitute the values of a is equal to 0 and b is equal to 1, if I substitute 0 complement of this and the b is equal to 1, 0 complement is 1, 1 into 1 is 1. So if I calculate the value of this means it will become 1. That means I have to combine these logical variables A and B with an invert operation such that when I substitute the values of these inputs means the output I should get is equal to 1. That is how the logical equations will be formed for a given input to get the output is equal to 1 like. So similarly, I have one more output here, that is when I give an input is equal to 1 and when is equal to 0 means the output I should get is equal to 1. So I will combine the logical variables like A and B bar. So whenever I give in both the inputs means I should get an output is equal to 1. That's why I will try to put a plus sign in between those terms such that I will be getting an output of an expression is equal to A bar B plus AB bar. For this we call it as an exclusive OR operation equation. So what I do is I will try to realize this expression by using a NAND gate only. NAND gate only. So just what I do is I will use the simple procedure here to realize it by using only NAND gate A B bar. So what I do is I will double complement this. If I do a double complement means the value will not change or the expression will not change like. As I said before, I will try to keep this bar, upper side bar as it is, and whatever is there below this I will try to simplify it like. Assuming that if I give any input to this NAND gate A and B means the output will be automatically inverted here like, for a given input. By assuming that I will try to keep this as it is and I will give this whole term as an input to this NAND gate, automatically it gives me an output is equal to an inverted one like. So now what I do is I will keep this bar as it is and I will try to simplify the inside equation by using a De Morgan's theorem like. So what I do is I will try to put A bar B bar dot, so plus will change to a dot product according to De Morgan's theorem. This is A B bar whole bar. I will not simplify this because you have already have a product terms between the logical variables like. Between the logical variables you should not simplify it because the expression with respect to NAND gate is a product term like. So I will try to keep this to this form and then I will realize it by using NAND gate like. So now what I do is I will take a first NAND gate for which I will try to short the input terminals like this A and so what is the output that I will be getting is A bar. Okay. So next what I will do is I will try to give B directly to this. So now the output that I will be getting is A bar is an input here, B is another input. So what is the output that I will be getting from this combination? It is A bar B whole bar. Similarly, what I do is this is B. So I will take this B, I will try to interconnect like this. This will become B bar, okay, and I will take this A and I will try to connect it to another gate like this. So what is the output that I will be getting? A B bar whole bar. See here I am by connecting one NAND gate I will be getting B bar, I am taking it is as it is and I will be connecting to a NAND gate like. So the output that I will be getting is A B bar whole bar like. Now because I wanted to combine these two functions here by using again the NAND gate only. So what I do is I will try to connect like this, I will get an output like this. See this is one input, this is another input, so I will be getting A bar B whole bar and A B bar whole bar. This is dot product, I will try to write it here. This is A B whole bar bar. So you have a bubble here like automatically it will be complemented. So you will be getting this is equal to A bar B plus A B bar. Just I will repeat the procedure how to do this means first take the expression which you wanted to realize it by using only the NAND gate means you double bar the given expression here like so that the equation expression will not change like. What you do is keep the uppermost bar as it is. So whatever the equation and the bar is there you try to simplify it by using De Morgan's theorem so that you will be removing a plus sign there in between the product terms like. When the plus sign is not there means you can realize it easily by using an AND gate operation. Don't simplify these product terms again like. So you try to keep it as it is and realize this expression, I mean the logical variables, if complement is there means you try to use the same NAND gate here and try to connect like this so that you will be getting the entire exclusive or expression by using only the NAND gate. Like, see, what I am doing is, if I am not using the NAND gate means I have to use one AND gate here, another AND gate here, and the third one is I have to use an OR gate. Like, that means you will be using two ICs here. One is with respect to an AND gate, another is with respect to OR gate. So that can be avoided by implementing only with a NAND gate. Like, that's why we call them as an universal gate. Whatever may be the length of the expressions, like, so I can implement only by using NAND gate, like NAND or NOR gate. That's why we specifically call them as universal gates. Like, so next we will see how to realize the basic gates, that is AND, OR gate and a NOT gate, by using NOR gate only, because as I said before, NAND and NOR are called as universal gates. Like, NOR gate realization, NOR gate. See, first we will try to realize the NOT operation by using a NOR gate. So what is an expression for NOT gate? This is y is equal to a bar. That is, a is one input variable, the output of that will be always a complemented one. Like, so now I wanted to realize this expression by using only the NOR gate operation. So as you know, the NOR gate, symbolic representation of NOR gate is the a, b. If I give an input a and b, means I will be getting an output is a plus b whole bar. This is an NOR gate actually. So what I need to do is, to get something like a NOT gate operation, you give the same inputs to the two pins here, like a and a. So if I give a and a, means I will be getting a plus a, this is equal to a itself. So I will be getting a complement term. Like, so in practical representation, what we do is, instead of giving a separate inputs to b as an a itself, you take an a input and will short it. Like, so this NOR gate now is working as a NOT gate. Like, this is just a NOT realization by using only the NOR gate. Like, so next what you do is, you will try to realize the OR gate by using only the NOR operation or NOR gate. Like, see, what is an expression in terms of an OR gate? This is a, y is equal to a plus b. Y is equal to a plus b. This expression I wanted to realize it only by using a NOR gate. See, now what I do is, see, I will take a NOR gate, I will give a and b as an input. So I will be getting an expression is a plus b whole bar. So what I do is, I have to get one more a complement term above this, means such that you will be getting a plus b. I will take another NOR gate and I will try to connect like this. So I will be getting a plus b. Bar is already there as an input to this gate. I will get one more bar, so that the output expression is equal to a plus b. This is y is equal to a plus b. This is an OR gate realization, like, by using only the NOR gate. So next we will see how we can realize the AND function, that is AND gate, by using only the NOR operation. AND gate by using only the NOR gate representation. Like, see, what is the function with respect to an AND gate? That is y is equal to a b. This has to be realized by using only the NOR gate. So what I do is, whatever the procedure that I use for an AND gate, NAND gate, that I will use it here. Like, see, I will put a double bar here. Like, if I put a double bar, means the expression will not change. Like, so this will be equal to I will keep the upper bar as it is, and I will try to simplify the lower bar by using De Morgan's theorem. Like, AB whole bar means it is A bar plus B bar. So now I have a plus term in between that. So if I have a plus term in between that, means I can realize it easily by using a NOR gate. Like, so what I do is, first I will try to get an A bar by using a NOR gate only. So what I do is, I will try to give A, and I to the NOR gate, means I will be getting bar, A bar. I will use another NOR gate. So I will connect B. So I will be getting B bar. So now what I need is A bar plus B bar whole bar. So I will try to connect like this. So, now A bar, because it is an OR operation, plus B bar, and there is a bubble here, naturally I will be getting A bar plus B bar whole bar. What is the final equation that you will be getting here? It is equal to Y is equal to AB. Now, the whole circuit output will be equal to 8B. This is nothing but the equivalent operation like an AND gate. Now, like this, you can realize the basic gates by using a universal gate, particularly NOR gate that I have realized now. Like, see, in terms of logic representation, we were using something like high and low. For one value, we were using high, and for 0, we were using a low. In terms of an electrical terms, high means it is a 5 volts, 0 means it is nothing but a 0 volts. See, we have two type of logic representation in case of digital logic. One is a positive logic and a negative logic. Like, so far what I have discussed is nothing but a positive logic. Like, for 1 we will be calling it as high, that is called as positive logic. 0 means it is a 0 volts. Like, we have another logic representation called as a negative logic. So, in negative logic, high means it is 0 and 1 means it is a low. It is an exact complement type of representation will be there. Like, see, just I will take an example, that is a truth table that I have given here, that is low means I will be getting an output is equal to low, and low high means the output I will be getting is equal to high. Just means I have taken OR gate operation. OR gate operation here, like, and I have represented by using a positive logic here, like positive logic. So, the high is nothing but 1 and low means the output is equal to 0. Here high is equal to, in a negative logic it will be reversed, like high is nothing but 0 and low is nothing but 1. See, if I change this a truth table in terms of negative logic means, as I said before, low means I have taken it is equal to low. So, the low means here it is nothing but 1 in case of negative logic. Here also B is low means the in negative logic it is equal to high. The output that I will be getting is 1 and the output is equal to 1 here. Like, wherever low is there means the value that we will be putting is 1, wherever high is there means we will be putting the logic is equal to 0. So, positive OR is nothing but a negative AND operation that we will be getting. This is advantageous in case of higher logic implementation. I hope you are understood. Like, so we have two logic representation. One is nothing but a positive logic, another is called as a negative logic. Like, so just I will repeat, in positive logic, high means it is equal to 1 value and low means it is equal to 0. In negative logic, high means it is equal to 0 and low means it is equal to 1. See, to represent these definitions we can write in terms of an voltage level with respect to the basic gates, positive OR and a negative AND. Like, positive OR is nothing but positive OR, OR is equivalent to a negative AND in case of negative logic. Similarly, positive AND a negative OR. Positive NOR, it is a negative NAND in terms of negative logic representation. That is, output is high if any one input is high. Like, okay. So, in case of AND gate operation, if both are high means the output will be equal to high, otherwise it will be equal to 0. So, it is a negative OR. Like, so for this, usually depending upon which logic that you will consider, we call it as an assertion level. Assertion level means, naturally, if I give an input is equal to 0 means that device should be activated, for which we call it as an assertion level, it is equal to 0. So, just I will try to read it out. To activate, if an input line has a bubble on it, you assert the input by making it low. If there is no bubble means assert the input by making it high. Huh? Right. See, just I will try to conclude it by saying that we have seen We have studied the basic gates like NOT gate, OR gate, AND gate, and an exclusive OR gate, as well as we have studied something like universal gates, NAND and NOR gates. So NAND and NOR gates are called as an universal gates. Why we call it as a universal gate means you can realize any type of the logical expression by using only NAND and NOR gates. The last topic that is left with is all these basic circuits can be implemented or expressed by using an HDL language, that is hardware description language. Hardware description language. So in the next class, just I will try to explain what is an hardware description language, what is its advantage, how to write a simple HDL model for these basic gates that you have studied in this session. Okay, thank you.